Now for an example to try on your own. So here we have the region that is in the first quadrant. It is bounded by the graphs of y equals x squared, y equals 4, and the y-axis. So it's that region in the first quadrant. And we're going to find the volume when we do three things. First, when you rotate this about the x-axis. Second, when you rotate this about the line x equals -1. And third, find the volume of the solid whose base is this region and whose cross-sections perpendicular to the y-axis are squares. So for part C, is like our lecture for Monday. This is the base of the region, and the cross-sections are perpendicular to the y-axis, and they are squares. So press pause and give those three a try. Oh yeah, and just write the integral. Don't actually compute the integral. Just write the integral that gives the volume. Okay, so here's part A, after you've had a chance to do those three out. So about the x-axis means this is our axis of revolution. There is a gap, right? This is the gap right here. Now at this one point, there is no gap, but only at a point. So if there's only a single point where there's no gap, then you still use the washer method. And when we write out the integral, you'll see how it doesn't actually come into play. So the washer method, because there is a gap, we have a horizontal axis of revolution, so we're in terms of x. And so our volume is the integral from a to b pi big R of x squared minus small r of x squared. A to b, it starts at 0. 0 is the start of our region if you're in terms of x. This is the end of our region. It's where y equals 4 and y equals x squared intersect. That's at 2. So it's from 0 to 2. Big R of x. Big R is the distance from the axis of revolution to the outside of the region. Top minus bottom, that's 4 minus 0, which of course is 4. Minus small r of x squared. Small r of x is the distance from the axis of revolution to the inside of the region, which is x squared minus 0. And so we do small r of x squared dx. And there you go. And of course you could simplify it. That's just 16 minus x to the 4th. But I'm not going to. That's the answer. Part B is actually also the washer method. I should have made one of these the disk method. Oh well. So x equals -1 is the axis of revolution. You can see the definite gap right there. So this is the washer method, where in terms of y, since we have that vertical axis of revolution, which means our volume is the integral from c to d of pi big R of y squared minus small r of y squared dy. The bounds. The bounds are in terms of y. The region starts at 0 and finishes at 4. So 0 to 4 are the bounds. The bounds are always where your region starts and finishes. Times pi. Don't forget that pi, by the way. It's the easy way to lose a point. Big R is the outside radius. Now the outside radius starts from the axis of revolution and goes to the outside of the region, the point farthest away. You're in terms of y, so it's the right side minus the left side. Now the right side is x squared, but we're in terms of y, so it's root y. So in terms of y, it's root y minus -1. Small r is the distance from the axis of revolution to the inside of the region. Right minus left, that's 0 minus -1. And there you go. Pi big R squared minus small r squared. And in terms of y, big R and small r is the right side minus the left side, where both are in terms of y. Now for C. So C, we have cross sections that are perpendicular to the y-axis. So for example, that is the bottom of one of the cross sections. That is the bottom of one of the squares, and the square is coming out of the screen. And we're going to add up all those squares. So the volume for part C is the integral from C to D of the area of each of those squares times how thick they are, dy, right? Because they're like infinitely thin squares. And their volume is the cross-sectional area times the thickness. And we add them all up from C until D. We're in terms of y, because that's the axis that we're perpendicular to. And it's because as you move along the y-axis, the base length of the square will change. So the area of the square is a function of y. It changes with y. So the area function, we have a square, so it's the base length squared. The base length is the right side minus the left side, which is root y minus 0. So it's just y, which is kind of crazy. The bounds are where you start and finish kind of lining up all these super thin squares. So you start to line them up at 0, you finish at 4. The area function is just y dy. Okay, we might do some more practice with this either in the next lecture or in our next live lecture, because this topic, volume, is one that always needs some practice before it kind of clicks into place and becomes more common sense. So we will do more with this probably in our next live lecture.